Right, welcome to 9.4. Today we're going to look at conditional and biconditional statements as they relate to our networking course. So, conditional statements is our first definition for this section. So, a conditional statement is again something that we use kind of with our logic unit. So, the phrase in English that we're going to use for conditional is if, then. So, we replace we use two simple statements for a conditional statement. So we're going to use our P and our Q here. Remember that they are simple statements, so they're declarative sentences that are either true or false. So our conditional, our connective that ties these two simple statements together is if then. So you may know that kind of phrasing from any science that you've done before. If then statements for hypotheses, for any kind of experiment. You may have heard this kind of phrase before. This is called a conditional. If P occurs, then Q occurs. So P and Q are any simple statements here. It can also be called an implication statement. So sometimes in like a word problem, you'll see implication in place of a conditional statement. But if P, then Q, or if your first statement, then your second statement. So the symbolic logic for this phrase, if P, then Q. So you just write your P, and then we have a right-facing arrow, and then Q. So instead of saying if P, then Q, all we write is P arrow to Q. Okay, so this is a one directional arrow. It must point to the right so that when you read this, it's if P occurs, then Q occurs. So you can also say for the implication, you can also write P implies Q. So if P occurs, then it's implying that Q is also occurring. So lots of different words to represent this type of statement. So we'll just go right into an example, and then we'll talk about the truth table for these statements. So our example here, P, our simple statement is it is raining. Q, our simple statement is pavement is slippery, or the pavement is slippery. We should put the in front of that. The pavement is slippery. So again, these are both declarative sentences that can either be true or false. It either is raining or it's not raining. The pavement is either slippery or it's not slippery. They're both sentences. So if I want to write P implies Q, or if P then Q, and I want to phrase it with these simple statements in English, that becomes if it is raining, then the pavement is slippery. So again, these two simple statements kind of make logical sense to us in English. However, I could replace these with anything, any simple statements. If the dog is running, then the pavement is slippery. If the sky is blue, then the world is round. Like, you could replace it with anything. It doesn't necessarily have to make sense. It's the logic that we're getting, like the symbolic logic that we're learning for these units. So some of your homework questions in the textbook are going to seem absolutely insane. That's fine. We're not judging the logical statement for its English representations. We're judging it for its symbolic logic and how we would apply that to any truth table, right? This is our generic cases that we want to be able to apply to any context. Okay, so we have our conditional if then. If I wanted to do the opposite order, so let's say I did Q implies P, right? Or if Q then P. Our English that way would be if the pavement is slippery, excuse my sloppy writing, please, then it is raining. So you'll have a few questions on your unit test that have you translate symbolic logic back into words and words into symbolic logic. So you need to be able to kind of go back and forth between this. And when we're translating our conditional statement from our symbolic logic to words. Remember that now we have 2 words to put in rather than our connectives and or not. We only had 1 word going in. Now we need an if at the beginning and a then as a precursor to our second statement. If-then statement. Okay, so conditional, also called implications. We're using our if-thens. Order does matter here very specifically. So you have to make sure the arrow is only pointing in one direction and that your simple statements match what you have in your symbolic logic, right? It's very easy to just read P, Q, and then assume that it's P implies Q, but you have to make sure it's not Q implies P, right? Be very cautious of what you're reading. So the truth table for this conditional statement, right? So we're just going to do our basic truth table for P implies Q. So again, we have our P and Q. So if we're doing the truth table for P implies Q, okay, we have 2 simple statements, right? So we have our 4 rows for 2 simple statements, which means we're going to have the same setup as we always do. Our first column is going to be first half true, second half false, and our second column will alternate true, false, true, false. Again, making sure that your T's and F's are nice and neat. If I can't read it, you will not get the mark. So then the conditional. So this is our new part here. This is the part we're concerned about. So P implies Q. So we have to be very cautious of the order here. We're saying if P is true, then Q is also true. So that's essentially what our conditional is. So if P is true, then Q is true. Right? So our first scenario here, P is true implies Q is true. That's a true scenario. If P is true, then Q is false, right? If P, then Q, but Q is not true, that's where we get our false. So we like this one. True implies false, we get a false, right? If it is raining, then the pavement is slippery, but the pavement is not slippery, that's when we get our negation in there. So true implies false is the only case where we're going to get a false for symbolic logic here. True implies false, not true, right? The whole premise of a conditional is the first one implies the truth of the second one. So this is our no case right here, our second one. So the last 2, and this is the hardest part to wrap your brain around, so pull your socks up. We have false implies true and false implies false. So again, think of what a conditional is. It's an implication that the first thing implies the second thing. If the first thing is already false, if the first part is already false, it does not matter what the second statement is, regardless of what phrase, what declarative sentence you're using. If the first one is already false, the second one is irrelevant. So for either of the last 2, and again, stay with me, the last 2 is going to be true because it doesn't matter what the second case is. The first one is already false. So whether it's a false statement implying a true one or a false statement implying a false statement, the answer, the implication becomes true because it doesn't matter what happens with the second one. I already know the first one's false. So whether it's a false implying a true or a false implying a false, we have a true logic statement because the conditional is no longer applicable. So their statement is void and we call it true. Okay, so this one is usually the trickiest one to understand logically. If you're uncomfortable with how we get to this truth table, just remember that there's only one case that gives you a false with an implication, and it's true implying a false. Everything else is true. Okay, sometimes students will choose to just memorize this last column, or just remember that that true implies false is the only time when you're getting false. Okay, so we're going to do another truth table for the same type of problem. We're going to do our, oh, I lost my pen, P and Q. But we're going to do Q implies P. So we have the same setup for our P's and Q's. True, false, true, false. Okay, so Q implies P. So even though the order, and again, we're not going to change the order of our P and Q in our initial 2 columns, But if I want to go Q implies P, so make sure that we're starting in the Q column and doing the implication towards the P column. Okay, so we have, it's going to follow the same pattern as these ones, or at least the same final answers, but it will be in a different order. So again, true implies true. We're okay with that one. False implies true. If it starts in false, I already know it's going to be true. True implies false. That's the only case where we get a false for an implication. And false implies false. Again, it starts with false, so my outcome is going to be true, regardless of what my second statement is going to be. Okay, so we have both options for our implication with two simple statements. So when we're doing kind of this opposite direction, so P implies Q and Q implies P, we call those converse conditionals. Converse. So converse, you might hear in context of English, conversely, so kind of opposite to. Conversely to his opinion, she agreed. That would be converse, so the opposite. So P implies Q and Q implies P are opposite directions of each other. Right? We're just kind of switching what the simple statements are. So we call those converse statements. So that's a new definition for us. I just like to think of it as reverse order or opposite for our converse. We also have two other kind of definitions that go with implications. We have inverse and contrapositive. So inverse, an inverse statement. So again, we're going to start with our standard P implies Q. This is our standard implication statement. So we know our converse is Q implies P, the reversed order. Our inverse is going to be a negation of both, but the same order. So we end up with not P implies not Q. Okay, so I like to think negates, but the same order. And I usually toss this in as a matching or multiple choice question for your test. So you do need to know these words. Anything that's usually bolded in my notes is going to be something that's going to come up on your test. Right, so inverse, negates, but it's the same order. So instead of our original conditional statement, we have the inverse, not P implies not Q. And the last one, our contrapositive. Okay, this one is a negation and a different order in the reverse. So it's our converse and an inverse. So it's not Q implies not P. Okay, so reverse, order, and negates, and your negations. Okay, so I always like to think the one that's the most work, so the negation and the reversed order, is your contrapositive, which is also the longest word. So longest letters, biggest kind of change to your original conditional. Okay, so if I have, let's do P is going to be you study, and Q will be you do well for some simple statements. Right, so if my P implies Q, so if I'm doing my conditional, our words will be if you study, then you do well. Okay, so our inverse, right, our inverse is going to be not P implies not Q. Our contrapositive is going to be not Q implies not P. Let's start with our converse though. So let's do Q implies P. Let's do our inverse of not P implies not Q. And let's do our contrapositive of not Q implies not P. So if you could pause the video and fill in these three statements with words. So again, our P is you study, and our Q is you do well. So pause this and go through those three compound statements, and then unpause and we'll go through it together. Okay, so hopefully you've tried them. Q implies P, so we're going to put if you do well, then you study. Not P implies not Q. So again, it's still a conditional, so I still have to start with if, but I'm going to include a not in my statement. So if you do not study, then you do not do well. And then our contrapositive, if you do not do well, then you do not study. Okay, so see all the different ways we can manipulate a implication statement or a conditional. So we can do our converse, reverse order, inverse, negations, but the same order, and our contrapositive, a combination of the reverse order and the negations. Okay, so lots of different ways that we can work with it. Again, you should know the words converse, inverse, contrapositive, what they mean in relation to what it looks like for symbolic logic, and how to apply that with words. Okay, so moving forward, again, if you have any questions at any point, please pop into our live session so I can work through this with you. But moving forward, hopefully we're all on the same page. Two statements are equivalent statements if and only if they have the same truth tables for every possible outcome. Okay, so two statements are equivalent statements if and only if they have the same truth tables for every possible outcome. Okay, so kind of think back to our set theory when we had equal and equivalent, right? Remember those definitions? So equal was that they were the exact same set, and equivalent meant they had the same number of elements in each set. So here equivalent is if they have the same truth tables for every possible outcome. So they may not be the same statements, they're not equal statements, they don't have the same combination of connectives and simple statements, but they're equivalent in that the outcome for those statements in a truth table is the same. So they're equivalent, not equal. Okay, so kind of everything links in this course. So think back to set theory. How did this relate to set theory? Just like our connectives kind of relate to our operations on sets. So if we have two simple statements that are equivalent, right? We've already kind of looked at those types of things. Do we remember this one from a previous lecture? Hopefully like, yeah, miss, I know what that symbol is. P, and this is not and Q, right? Or that NAND, N-A-N-D, right? So we have the and symbol with that almost like a complement over the and symbol. So it's the negation of our and. So we know that this symbolic phrase is the same as the negation of our and. So we can say that is equivalent to the negation of our and column, right? These two compound statements are going to have the same truth table, right? The same last column for their truth table. Same thing with our P nor Q. That's going to be equivalent, spell words, equivalent to the negation of our or column, right? So when we're showing equivalence, when we want to show equivalence, because again, we remember math people are super lazy, but super efficient. So we don't want to write is equivalent to, and as you can see, poorly written it anyways. If I don't want to write this, we instead use a symbol, which we call the biconditional. So instead of writing is equivalent to, we take this if and only if portion, is equivalent to, and it becomes this symbol. So it's a double-sided arrow, which means that I could say it is conditional in one direction and conditional in the other direction, right? If and only if. So if then for the regular implication, and if then for the converse going in the other direction. So I get this biconditional symbol, and it will show equivalence between either side of that arrow. Okay, so I can replace these two statements with P NAND Q biconditional to the negation of P and Q. And I can do P NOR Q biconditional with the negation of P or Q. Excuse me. All right, so I can replace that is equivalent to, or the if and only if, with this biconditional symbol that shows that these two statements on either side of my biconditional are equivalent. They're going to have the same ending outcome for our truth table. So we can even just kind of complete a biconditional statement with a truth table, as everything here is going to be with a truth table. So we have P and Q, and we're going to do P biconditional with Q. So in the case that they're just simple statements. So again, P and Q, we have two simple statements. We're going to have 4 rows. Our first 2 columns are always going to remain the same. P is going to be first half true, second half false. Q is going to be alternating true, false all the way down. Excuse me, my voice is going. Okay, so P biconditional with Q. So remember, this is an implication in both ways. So our first implication was we needed a true implies true or false implies anything for it to be true. But now I also need the Q implies P to also be true for this biconditional. So I need it to be a true conditional statement in both directions, which means true implies true and true implies true. That will work. So my first row is always going to end up being true. So my second row here, if I do P implies Q, I have true implies false. That gives me a false. So no matter what, my second row is going to give me false. Okay, my third row, if I do P implies Q, I have false implies true. So normally that would be a true, but I also have to go in the converse direction. So conversely, Q implies P, and then I have true implies false, which gives me a false, just like my second row. This one, the converse, is going to give me false. Right? And my last column, false implies false, would give me a true, and then conversely, Q implies P gives me false implies false, so I also get a true. So a biconditional is going to be true when you have the same values, right? So when I have both true, I get a true, and when I have both false, I get a false. But any combination between those two, one of my statements for the conditional, either the converse or the regular conditional, is going to give me a false. So again, we can kind of say as a kind of cheat sheet for biconditional, it's true when both values are true. When both values are true, or both values are false. So I just say it's true when both values are the same. Right, and this is kind of opposite to what we had for exclusively or, right? Remember this guy, exclusively or? That was true when you had exactly one true in your row. So that would be the 2 cases here where we get false. Biconditional is true when you have both values are the same. Okay, I think that covers everything that I wanted to do for biconditionals. Yeah, so combining 2 statements with a biconditional, if they're equivalent, we'll end up with a tautology. But let's go into some examples so we can see that right off the bat. So let's go into some examples. Okay, so our first one here, we're going to, let's do this one. So we have P biconditional with Q. Okay, so I'm going to put that in brackets. I'm going to do another biconditional with the negation of P exclusively or Q. So this is my entire statement here. So this is a nice big biconditional statement. So first thing we always do, and again, I've done these grids for you, but if you were handwriting them on your own, you would say, first question, how many simple statements do I have, and how many rows will I need in my chart? So I have P and Q only. I have 1, 2, 3, 4 connectives, so I'm probably going to want 4 columns, 1 for each connective, and P and Q to start. So I always like to get the P and Q out of the way. So we have true, true, false, false, and our Q alternates true, false, true, false. Okay, then we can layer in our connectives. So I have P biconditional with Q is my first kind of connective. Then I can't take this middle biconditional. I can't do this one until I've completed everything on the right-hand side of it. Right, this connects both of these together. Just think of your BEDMAS with brackets. You want to do your innermost brackets first and work your way out. So I have to do these inner brackets as well. So I'm going to do P exclusively or Q. Then I'm going to do the negation of P exclusively or Q. And then my last column, if you remember, I can put all to encompass this entire phrase, or I can write it all out. So I'm going to write this whole one out here. So P biconditional with Q, biconditional with the negation of P exclusively or Q. Okay, so that's everything. Or you can put all. Okay, that's the only column that I'll allow you to shorthand. Everything else should be written in your column titles. So filling in your tables. So a biconditional, remember, is true when we have both values the same. So my true and true and my false and false will give me trues, and everything in between will give me a false. Exclusively or, right? We have or with the kind of complement on the bottom. So it's not the negation of or, it's exclusively or, which means I need at least one true for it to be true. So that means my middle ones are true and my other two are false. Okay, then the negation of the exclusively or column. So we're going to take the opposite of what we had here, which gives me true, false, false, true. So remember we said that if two statements are equivalent, they will have the same two columns in their truth table. So true, false, false, true for our biconditional, and true, false, false, true for the negation of our exclusively or. Those are the same column. So we know that these two are equivalent statements, but to show equivalence in our logic functions, we connect them with a biconditional, which is what we have here. And when we do that, remember, a biconditional is true when you have the same values. So if I move forward in my last column, I'm connecting these two statements with a biconditional. True biconditional with true gives me true. False biconditional with false gives me true. False biconditional with false gives me true. And true biconditional with true gives me true. And what did we call this type of column? Remember last maybe 1 or 2 lectures ago, what did we call this type of column? It had a specific word, tautology. Right? When my column is all true, it's called a tautology, or a lowercase t, tautology. So when you connect two statements, whether they're simple or compound, with a biconditional, and you get a tautology, it means that those two statements are equivalent. So sometimes you'll get these beasts of compound statements, just hideous, huge compound statements, and you have no idea whether or not you're going to get whether or not they're equivalent. You do a giant truth table, you go through all the steps, you figure out all the end, and your outcome, your all statement, ends up being true for everything. You know that those two statements, so this guy and this guy, are equivalent statements because you get that tautology. So this is kind of our way of proving something is equivalent. So I could follow this up with a therefore statement. Therefore, these two statements are equivalent, kind of however we go through it. and we'll be doing arguments later in this chapter as well. And that's not just proving equivalence, but proving a property of logic, or arguing with hypotheses and conclusions. So this kind of builds from our theory here of equivalence and how we show that within a truth table. Okay, so now I'm going to speed up and we're going to go through a few more examples. Now that we've done a nice slow one to start. So our example B, we're going to do big bracket, small bracket, P implies Q, and Q implies P. So that's all together, biconditional with P biconditional with Q. So when I'm doing something with biconditionals, for my peace of mind, I like to put either side of my biconditional in big brackets. That just helps me visually to separate the left and the right hand side of my biconditionals. Okay, so we have P implies Q and Q implies P, so that's one compound statement is biconditional with P implies Q and Q implies P. So that's our biconditional, or we can say if and only if as well. So we have P and Q as our only simple statements. So we have true, true, false, false. Hopefully these seem familiar to you now. True, false, true, false. Then working through my left-hand bracket here, I'm going to have P implies Q and Q implies P. And then I'm going to have both of those together. So P implies Q and Q implies P. Okay, hopefully you can be a little bit neater. It is hard writing on this tablet. And then I'm going to do my right-hand side. So P biconditional with Q, or P if and only if Q. And then everything together, I'm going to put all. Okay, so P implies Q. So implication, this is one direction of implication, which means we're only going to have one false, and that's the case when true implies false. Everything else is going to be true. Same thing for here, Q implies P. So remember, we're starting in the Q column and looking towards the P column. So again, the only case where we have a false is when true implies false. So that's in the third row here. Everything else gives us a true. And then combining these two together with an and. So I'm looking at my third column and fourth column, combining them with an and. So refer back to our very first or second or first lecture on this. And is true when you have both true. So I have a true, a false, and a true. And then our biconditional again is true when we have the same. So true, false, and true. So again, I can already see that these are equivalent statements, but to actually prove fully that they are equivalent statements, I do need to get that tautology with biconditional. So our full statement biconditional with our two compound statements. So putting these two together with a biconditional, true when they're the same. So we have true, 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 and true. Okay, true and true, false and false. So we get the same column, we end up with a tautology. Therefore, I can say that these two compound statements are equivalent. Okay, that won't always be the case. We're just starting with some easier examples. So let's move on to C. So C, we're going to have P biconditional with Q, or not P and not Q, but our first not's outside of the bracket. And then we're going to put biconditional with P implies Q. So again, I like to toss some big brackets around my biconditionals so that I know my left side and my right side. So we're going to have P and Q. I don't think I gave myself enough columns here, so I'm going to kind of add one in, not Q, for that one there. I'm also going to need P biconditional with Q, not We want our and in there. P and not Q, not P and not Q. P implies Q. I think that covers everything. Right? We have our not Q, P biconditional with Q, not P and not Q, not P and not Q. Oh, we need everything together on our left-hand side. Yeah, I skipped a couple things in here. Okay, so let's add in one more at the end here. This will be our all. And then I'm going to clear this one out so that I kind of have them in order. This would be my P biconditional with Q, or not P and not Q. This will be my P implies Q, and then I have all in my last column. Okay, so we have true, true, false, false, true, false, true, false. Not Q is going to be the opposite of our Q column, so we have false, true, false, true. P biconditional with Q, right? That's our first two columns here, and we're looking for the cases where they're both the same. Everything else is false. P and not Q, so again, our first column, and our not Q column, our third one that I've kind of makeshift put in here, combined with an and, so I need both of them to be true. We have false, true, false, false. Not P and not Q, so again, taking the negation of the column we just did, we have true, false, false, false. Combining the biconditional, so now we're looking at this one with our negation of the and, so that one here, and we're connecting this with an or. So layers of complexity with all of these connectives. So when I'm connecting these two columns with or, we're looking for at least one true to get us a true. So we have true, false, false, true. Our conditional P implies Q. Again, be very careful of your direction. P implies Q is only false when you have that true implies false. Everything else gives us a true. And my last column, so I'm connecting my conditional that we just did with that big or column or compound statement that we had from the left-hand side of our biconditional, and we're connecting that with a biconditional to prove equivalence. So we need them to be the same value. So true and true gives me a true, false and false gives me a true, false and true gives me a false, and true gives me a true. So these two statements we can say not equivalent. So these two compound statements are not equivalent. Okay. We could also have this phrased, so if this question C was phrased in like a word problem, right, I could say, is P biconditional with Q or not P and not Q equivalent to P implies Q? So I could have phrased it like that. Actually, let's put that up there so it looks neater. Looks messy. Let's fix it. 2P implies Q. So I could have phrased this as your test question. Is this compound statement equivalent to this compound statement? And then you would have to show me the truth table, get that final column to show me, no, they're not equivalent. I have a false with my biconditional. Okay, so you have to get to this final column to prove that two statements are equivalent. Again, you're going to use the biconditional. You're going to take those two statements, you're going to squish them together with your biconditional, just like you see here. Follow through that entire statement with the truth table and get that final column. That will show you if it's a tautology, you have equivalence. If it's not a tautology, you do not have equivalence. Okay. Now, it's not always going to be problems where I'm asking you to prove whether two things are equivalent or not. I may just ask you for the truth table. For example, we're going to do a bigger truth table, but this one's not proving that anything's equivalent. I could just say, show me the truth table for the following statement. So we have P implies R and big bracket, small bracket, P if and only if Q exclusively or R. So I could just say develop a truth table for this statement. Okay, it's not always showing equivalence. So the only thing that kind of would show equivalence here is our biconditional within this small bracket, but that's not the entire thing. So be mindful of how your brackets are laid out. Our big connector here is this and. Okay, so if I'm setting this up, how many simple statements do I have? I have a P, a Q, and an R, which means we're working with 3 simple statements. Okay, if I have 3 simple statements, that means I'm going to have 8 rows, so I like to fill these in first. Right, for our P, we have the first half are true, second half are false, so that's 4 trues, 4 false. Q, we're going to have 2 true, 2 false, 2 true, 2 false. And our last column is going to alternate true, false all the way down until we have our first 3 columns done. Then we can layer in our connectives. So I'm going to start on the left and work my way forward, as well as doing any inner brackets first. So the very first bracket I have here is P implies R, so I can get that one out of the way. I can't do this and until I know what this compound statement is going to be, and I can't do this exclusively or until I know what this inner bracket is going to be. So I have to start with that biconditional, and then I can do my biconditional Q, ooh, probably should put the Q there, with my exclusively or R, and then I can put everything together here. So I can do my P implies R and P biconditional with Q exclusively or R. Or again, I can phrase this as all. Okay, so working through our truth table now. So this one's not proving any equivalency, it's just filling in our truth table. So our first filling in column here is P implies R. So if you were the one that was memorizing the 4 cells that we did for the previous tables, right, we have to think back to what is a conditional, because now I'm doing P implies R. So I'm looking at these 2 columns here. Implication was false only when you had true implying false. So I'm just going to go through my rows and look for that one scenario. So true implies true gives me a true. True implies false gives me a false. True implies true gives me a true. True implies false. Again, that's the scenario we don't want. And then the last half all starts with false. So regardless of what the second entry is going to be, they're all going to be true, right? If we start with false, it doesn't matter what happens after. We're already starting on a false premise. We end up with true. Okay. Biconditional, when we have the same values. So true and true, true and false, true and false, false and true, false and true, false and false, false and false. Okay, again, any issues up to this point, pop into our live session. Okay, moving forward, now we do our biconditional. So what we just did in our last column, we're doing exclusively or with R. So I'm looking here and here. So exclusively or, for that to be true, we need exactly 1 true. So true and true will give me a false. False and true will give me a true. True and false will give me a true. False and false will give me a false. True and false will give me a true. False and false will give me a false. True and true will give me a false. False and true will give me a true. Okay. Just double checking my work here. False, true, false, false, true. Good. Okay, so then everything all together, we're connecting these with an and. So now I'm looking at my and is connecting the P implies R, so that's this column here, and my big bracketed right-hand bracket, so that's going to be this one. So I'm connecting these 2 with an and, so I'm looking for both values to be true, which gives me false, false, true, false, true, false, false, true. Okay, and that's it. So that's just a completed truth table using some of our new symbols. So using our both conditional and biconditional. So you've learned kind of 2 new topics here along with some new definitions, right? We know, just kind of scrolling back through what we did today, we know what a conditional is, an if-then statement, right? We know how to fill in the statement in a truth table. We now know the definitions conditional, converse, inverse, contrapositive, equivalent, and biconditional. We know when we use the biconditional to show equivalence, how we set that up in a truth table, right? We know how to prove equivalence, we know what a tautology is, and we know how to do any kind of truth table involving our new symbols of conditional and biconditional. Okay, so some practice questions for you here. We have page 245, questions 1 to 28 and 35 to 40. Please try all the odd ones, check your answers in the back of the book, and let me know if you have any issues at all. I will see you in the next lecture video.